Welcome to the first week of our second grade PD module on operations and algebraic thinking. The cluster that we're going to be examining this week is represent and solve problems involving addition and subtraction. Now, while we've always wanted students who are good problem solvers, the Common Core standards set a high bar for meeting that expectation, and they expect mastery of all addition and subtraction problem types by the end of second grade. To achieve this will require us to be more intentional than ever in our teaching and to carefully consider how to scaffold that learning journey. There's quite a bit of information packed into this first standard under operations and algebraic thinking for second grade, particularly when we look at it in light of the Common Core progressions, which the Common Core writing team wrote as an elaboration of the standards. The progressions document, which is also in our resource library, serves as a companion document. It sheds a lot of light on the intent of the standards, and we're going to be referring to it often. Second graders are going to be working with one-step problems and two-step problems, and they're adding and subtracting within 100 using all of the problem types and subtypes. They're expected to make sense of mathematical relationships which are embedded in words and to be able to convert them into representations such as diagrams and equations which actually match the situation. The work that second graders do in operations and algebraic thinking follows naturally from concepts that were developed in first grade, but there are some obvious extensions. Children in first grade were introduced to a variety of problem types and subtypes as listed in the Common Core appendix. You're going to see a chart of those in just a minute. The first graders were to work with all of those problem subtypes and to master most of them. The remaining subtypes that they might not have mastered, which were identified in the progressions, are the hardest problem subtypes. They're expected to be mastered in grade 2, especially at least with single-digit addition and subtraction. So while some of the problem types are expected to have much higher numbers, the hardest problem types are still expected to have mastery at second grade level, although those can have single-digit numbers. The easier and medium difficulty problem types also serve an important role in the curriculum. They're used to foster 2 additional shifts in second grade, working strategically with larger numbers and solving with two-step problems. The two-step problems are going to be the focus of our next lesson. Another important second grade goal is for students to develop their capacity to represent problems through diagrams and equations. That's a theme that we're going to come back to several times this week. Action problems are one of the types of problems that are in the Common Core appendix, and these problems are characterized by having a starting quantity, a change. The change can involve either a take-from action, a separating type take-from action, or an add-to-join action. But there's some kind of a change. That change results in a new quantity. So you have a result quantity, a change quantity, and a start quantity. And those represent the position of the unknown in the problem. So we have 2 types of action, add to or take from, and 3 possible positions of unknowns, whether it's the result, the change, or the start. So that's the classification system that's being used here. Quickly, I would just like to point out that the first column, the result unknown, are the easiest, and those were introduced for the first time in kindergarten. The change unknown problems were introduced for the first time in first grade. They're considered medium difficulty. The start unknown problems are extremely difficult. You'll see that they're partitioned off here. That's to illustrate that not all first graders will have achieved mastery, but they are expected to achieve mastery in second grade. The non-action problem types involve put together, take apart, which I also think of as part whole, and the compare problems. If we take a look at the top row, that's those part whole problems. There is essentially a whole set that's partitioned off into 2 smaller sets. Nothing's being joined, sold, bought, or given away, so there is no action. Kindergarten children were introduced to the total unknown, which is in the first column, and the both add-ins unknown, which is in the last column. The both add-ins unknown is essentially decomposing numbers, taking a number and finding many combinations. So they started doing that in kindergarten. The middle one you see here, add-in unknown, was introduced in first grade and would be a medium difficulty problem. Compare problems are in the bottom row, and they were introduced for the first time in first grade. They tend to be rather difficult for children. There are a variety of reasons for this difficulty, but within this hard group, there are two particular problems partitioned off that are even the hardest within this group. And the reason for that is that the language embedded in the problem is a bit misleading. It would perhaps lead a child to think that the opposite operation is required. Now, although first graders were expected to work with these tough problems, again, not all of them will have mastered it, and the Common Core lists second grade as the year in which they will be mastered. If you were counting, you might have noticed that children are expected to master 12 different one-step problem types by the end of second grade. That sounds intimidating, but keep in mind that these were to have been mastered, many of them were to have been mastered in first grade. Some of them were introduced as early as kindergarten. It would, however, be helpful for your school to have some kind of a tracking system by which you record how students are doing in response to all these different problem types. Because children are at different levels of mastery for different problem types and for different sized number sets, I encourage you to think strategically about how you're using word problems as instructional tools. For example, when children are given simpler problem types, then they should be stretched intellectually in other areas, like working with larger number sets and building place value strategies, or learning how to apply mental math strategies with numbers within 20. So consider using those simple problems to build some other skill that's a target for second grade. And then if you have a really hard problem type, that's going to take a lot of cognitive load. So try to make the other things very clear, very familiar context. The context makes sense. The wording is very clear. There's not a lot of extraneous or misleading information there. The number sets tend to be pretty low. Therefore, all of their cognitive load can really go into this making sense of the problem type. For all 12 problem types, however, there needs to be an effort to get children independently representing these problems through diagrams and equations. Now, when I say independent, that's our end goal. Just by expecting it doesn't get them there. It will require a process that involves modeling, scaffolding, and independent practice with feedback. We're going to look at some examples of the hardest problem types. You might notice that the number set here is very low for second graders. That's a good indication that the actual problem is rather hard. It is a start unknown problem. As you read the problem, you might notice that there is a take from action in the problem, so that would cause many children to feel like it's subtraction-like. Indeed, the situation equation that you see here is a subtraction number sentence. If we were to exactly write what's happening in this problem in an equation that exactly matches the problem, it would actually be blank, we don't know the starting quantity, minus, there's a take from action, 7. That's how many were taken away, results in a quantity of 5. So the situation equation is given there. However, the situation equation doesn't necessarily lead you to see that this is an addition problem, really. And it's in situations like this where visual representations are worth their weight in gold for helping students to see that it's addition. They will likely struggle and want to know what operation. If you tell them that it's addition, you might as well have not even bothered giving them the word problem and just said, please solve 7 plus 5. It ceases to be a problem at that point. We have to get students to the point where they can see for themselves what operation is required without giving them the wording saying try addition. We can't do that. Otherwise, they will run into problems. So we're going to think about how to use some visual tools to illustrate that. And we're going to come back to that in a minute. But first, I want to actually show the other really hard type of problem that second graders are expected to master. And that's compare problems with language variants that are somewhat misleading. So in the first problem, the word fewer would cause many students to want to subtract, but it's actually addition. And in the second problem here, the word more might lead students to think that they should add, but actually they should subtract. The only way you're going to get students to begin to see how they should not be pulling these words out superficially and making a judgment is by giving them problems like that. They have to see that the clue word isn't going to be helpful to them so that they go deeper in trying to make sense These representations that you see here are called tape models, and they are, or tape diagrams, they are specifically mentioned in the Common Core progressions as a useful tool for illustrating mathematical relationships. When you study these visual tools, you will notice, I think, that it becomes obvious what operation is required by the nature of the representation. So that's what we want students to be able to do, is to look at representations and see what operation is required for themselves without us having to tell them. And we definitely want to move them beyond superficial cues. By the end of second grade, we want our children to be able to read a word problem, decide for themselves what operation is required, and for some simple problems, this may just quickly be able to result in an equation. So, yep, of course I know exactly what's going on, and this is the equation that matches it. But for the more difficult ones, the students really need to see visual representations as a useful tool that will help them to explore and find out what operation is actually required. More than ever, the emphasis now is on training children to understand mathematical situations on their own. And for teachers, that means our challenge is to scaffold a process by which they're going to get to that point. We can begin by making sure that we put enormous value on understanding the situation and taking time to visualize it, perhaps even to draw a model before we try to do something with the numbers. We also put value on ensuring that children can make connections between how does this model match the problem, how does this equation match the model, pointing to this numeral in the equation, what does that represent in the problem? The standard also specifies that children learn to write equations with symbols, and the symbol is relatively unimportant here. I remember a few years ago I was talking with a homeschooling parent who was just thrilled that she was teaching her first and second graders how to solve for x. Well, the letter x is not some magical ingredient of algebra. It is really not any more cognitively difficult to solve for x than to solve for question mark or to solve for empty box. But it is a good idea to use a variety of symbols for the unknown so that the children develop some flexibility and understand that the symbol is really a place marker that just means we're searching for, what number would make sense here to make these statements or equations true. If they have only ever seen it one way, they're less likely to be flexible. I've been primarily highlighting the difficult one-step problem types which second graders are expected to master, and you will see that in these situations the clue words are counterproductive to the solution. Children, in the true nature of basic human nature, will often want to take the easy way out and make a snap judgment as to what to do, even while they're still reading the problem. So I spend part of my time just trying to slow them down, take time, make sense of the situation, and drawing visual models is one useful way to slow them down. And so by expecting that out of my learners, I'm basically saying, don't jump to the next step. Take your time here. In addition to the tape model, another model that I use quite a bit is the number bond. A general additive relationship involves two addends and a total, which I introduced as parts and a whole back in kindergarten. The general model illustrates that a whole can be partitioned into two parts, and in second grade we want students to understand the nature of operations in a deep and meaningful way. So instead of thinking that subtraction is subtraction because it's takeaway, well, not all subtraction is takeaway, so that perception will get them into difficulty. Instead, we want them to develop a more robust understanding that addition means I know two parts and I'm searching for the total or the whole. Though, if that's the situation, it obviously is addition. Subtraction, I know a whole value and I know one part of it, but it's the other part I don't know. Oh, well, that must be subtraction then. If they can generalize and see this pattern, they will more easily be able to make judgments based on mathematical relationships rather than based on their feelings about the kind of action that's going on. Here you see that the number bond is such a useful framework that you can use it for many different kinds of problems and problem types. And most of these ideas we've discussed already, but I want to draw your attention to the comparison number bond on the bottom right. compare problems are really difficult for children. There's no action. The idea of what is the difference between two numbers is abstract for them. So beginning with concrete representations and then modeling with a number bond, you can support children in beginning to see that if you take the larger quantity that you're comparing, it can be decomposed into two parts, the part that is the same as the smaller quantity and the part that is the extra. It's the how many more, it's the difference. And by starting with concrete and then modeling this relationship with a number bond, they can begin to more concretely visualize what a difference is, what is meant by the how many more. The two models that I've referenced in this presentation are number bonds and tape diagrams. These two models are specifically mentioned by Common Core authors. And the progressions also discusses these tools in the first grade section as well. So your learners might come to you with some background in using those visualization tools. If not, I highly recommend that you begin by introducing them first through concrete, and then you model what you just did concretely with the tool, making connections back and forth so that the representation has meaning for them. They understand what these things represent. To give you an example of this, let's return to the Yolanda problem that was a start unknown. If you were introducing these visual tools, you would begin with concrete modeling. So you might actually get some golf balls out and have children try to act it out. And one of the first things they'll notice is they don't really know how many she had in the box. Oh, you didn't know the starting amount. So you can actually begin to build this through your sort of difficulty in acting it out with the golf balls. Then you can build this number bond. As you build the number bond, you want students to attend to the mathematical relationships. The goal isn't really to find out how many golf balls she had in the beginning. I mean, that is a response, but the real goal is to understand mathematical relationships, to understand the nature of addition and subtraction more deeply. And so in this case, that number bond allows you to do that. It isn't just can they get the answer, it's do they perceive that this is addition, and what is it that makes it addition? Now you're getting at the deeper understanding of the content, that I know two parts and I don't know a whole. And the number bond and the tape diagram both illustrate this component. I'm not going to say a lot about equations at this point because we're going to focus more intently on that at the end of the week, but I do want to just follow up with this Yolanda problem by illustrating how the problem is represented by an equation. The Common Core authors talk about the need for students to write situation equations that exactly match the problem. In this case, we don't know how many she had to start with. Some were taken away from that point. And so our number sentence has to start with the unknown, and then some were taken away, 7 were taken away. So it's question mark or x minus 7 equals 5. That's a situation equation. Sometimes they can be solved immediately, but in this case, we actually have to convert it. It's not really in a format where we can easily solve it. So we would have to convert it to 7 plus 5. Now that's really basic algebra, okay? But we're not going to teach second graders, well, subtract 7 from both sides. And these rules have no meaning for them at the second grade level. So how do you get first graders to do algebra without teaching them algebra rules that have no meaning for them? Well, let's back up. You do it through the models. In this case, they can see the number bond that involves a part that's 7, a part that's 5, and a whole that's unknown. And they can say, oh, look, these two equations have the exact same number bond. They mean the same thing. So through the visual tools, you can actually get them to do algebra without any of the so-called rules of algebra. Getting children to accurately draw number bonds and tape models that match the situations and to accurately translate words into equations is clearly something that's not going to happen overnight. Children need to see many kinds of problems modeled so that these visual tools can just become internalized over time. They need opportunities to grow in their capacity. Early in the school year, I spend a lot of time modeling, and in the independent work that I give to them, I actually provide them sort of skeletal models that they can fill in the numbers. They have to decide where where does this number go? What would make sense for the problem? So they still have some cognitive load there to exercise. I'm not making it easy, but there is a structure for them to begin to work with. And then over the course of the year for the easy problems, that goes away and they have to build a model from scratch. I still provide the scaffold for longer based on problem difficulty and eventually phase those out so that they're doing the modeling on their own of the problem. Recognizing that you're working on long-term skills development, it is really unfair to expect immediate perfection. Children also benefit by seeing other children's representations and trying to make sense of their thinking. So build in a long-term developmental aspect where they get feedback on their own work, they critique their other peers. Look at the model this person's drawn. Does this actually match the problem? What would you say? What advice could you give them for how to improve it? When you do that, you're actually getting at Mathematical Standard of Practice 3, where they're critiquing other people's reasoning. You can also clearly, through all that we've talked about in this presentation, see that we're talking about Mathematical Standard of Practice 1, really making sense of problems. And that making sense of the problem allows you to persevere. And then finally, building models that match situations. Those models include diagrams, but they also include equations. And that is Mathematical Standard of Practice 4.